In this lesson, we're going to take a look at radioactive decay. That is, the rate at which radioactive decay occurs. And this is different than a chemical reaction because when nuclear decay occurs, it's a steady rate, and we can't really do anything to change it. Not like a chemical reaction that we can heat up or stir or throw in a catalyst to change the rate of the decay. In a nuclear reaction, it happens at a very steady rate. And the unit we use to measure the rate of a nuclear decay is called half-life. Half-life is the amount of time it takes for half of the material to decay into something else. So if you started with 4 grams of radioactive material, after one half-life, say it takes 10 years for half of it to decay, after 10 years you'll only have 2 grams of that radioactive material left. The other 2 grams changed into something else, or emitted all its radiation, it decayed and is now more stable. Then, after another 10 years, you'll have 1 gram left. So it doesn't go half zero. It goes half, then half of that, and then after another 10 years you'll have half of a gram left, and after another 10 years you'll have half of a half, which is a quarter, right? And so this continues on through. So not every isotope has the same half-life, but they all go through the same decay rate. So this could be 10 years, it could be 100 years, it could be seconds, depending on what the radioactive isotope is. After a time of one half-life has elapsed, the amount of original radioactive material is cut in half, and then the process proceeds. Now, because we can have different decay times, we have different stabilities. 10 years is actually not that long of a half-life. Some things have half-lives of millions to billions of years, but other things also have half-lives of less than a nanosecond. So, depending on what radioactive isotope you can have different decay rates. The shorter the rate, the more unstable it is, and the more rapidly it decays into something more stable. The longer the rate, the more stable the isotope is, and the longer it takes for the decay to occur. Now, let's take a look at what that means. So polonium-218 has a half-life of 3 minutes. That means every 3 minutes, half of that stuff is going to decay into a more stable isotope. So after one decay, 3 days has elapsed, or have elapsed, and that means we only have 50% of what we started with. And that means we have half of what we started with. Okay? After 2 decays, that takes another 3 days, which gets me up to 6 days total. We only have 25% because half of 50% is 25%, and that's a quarter of the original stuff remaining. After 3 decays, I'm up to 9 days, right? Because or not days, this is minutes. So 3 minutes, 6 minutes, 9 minutes, and then half of 25% is 12.5%, and half of a quarter is an eighth. And then 4 decays, we go, let's see, 12 minutes, another 3 minutes have elapsed, and half of 12.5 is 6.25%, and then half of an eighth is a 16th. And you can see this just continues. So our next decay takes 3 more minutes, so that's 15 minutes. And then half of that is 3.125%, and we'll be all the way down to a 32nd of what we started with remaining. So these numbers right here, these are just telling you mathematically how to do this, although the table is generally pretty straightforward, easy way to get this done. So initially we start with some amount, 3 minutes later we have half of that, 3 minutes after that we have half of that, 3 minutes after that we have half of that, 3 minutes after that we have, okay. And so this is always going to stay the same no matter the half-life, this is always going to stay the same no matter the half-life, this is always going to stay the same no matter the half-life, but the different half-lives will actually affect the amount of time elapsed. This matters if you're trying to use radioactive decay to figure out how old something is, which is actually something scientists do. We can date something based on how much radioactive material is left compared to its decay products, or compared to the known amount it should have had. So some things that have different decay rates are useful for dating different things. The age of the universe, we use things like uranium-238 because it has a half-life of 4.5 billion years. Our sun is only about 4.6 billion years old, so that works. If we need something that's a little bit less old, 700 million years, uranium-235, still an incredibly long half-life. Then carbon-14, we're down into thousands of years, and there are hundreds of isotopes that fall in between here. Carbon-14 is especially handy because we can use it to date things that used to be alive. Tungsten-187, this one has a half-life of about a day. Radon-220, a half-life of less than a minute. And then astatine 215, which has a half-life of zero point 0.1 microseconds or 0.0001 seconds. And there are hundreds of more isotopes that fall, some higher than this, some lower than this, and lots in between. So astatine 215 here would be the most unstable because it has the shortest half-life. Uranium 238 has the longest half-life and is therefore the most stable of the ones listed. Okay. Now, radioactive dating, we actually use the half-life table to figure out how old something is based on what's left in it. So we use decay rates to determine the age of a sample. Carbon dating works for things that used to be alive because carbon-14 is actually created in the atmosphere by cosmic rays bombarding nitrogen. So nitrogen gets hit with cosmic rays, which converts it into carbon-14. And then animals and plants take that carbon in, and it's trapped in those things, and then they die and they decay, and the carbon-14 decays. And by measuring how much carbon-14 is left, we can figure out how long ago it died because we know how much carbon-14 it should have had based on the amount of carbon-14 in the atmosphere. Because once it stops taking in carbon, the amount of carbon-14 is no longer going to increase. Not everything works quite so handily because we know what the starting amount was for carbon-14. We can figure out how old something is. For other materials, we have to look at the abundance of the radioisotope compared to how much of its decay products are present. So we know that uranium decays into lead. So if we measure a sample and we figure out what the ratio of lead to uranium in it is, we have a pretty good idea of how long it's been decaying and therefore how old it is. Now, let's take a look at an example problem. This is basically just going to be like filling out your own table. Iodine 131 has a half-life of 6 days. How old is a sample in which only 3.125% of the original remains? So let's see. We know I'm going to go with age for one column. I'm going to go percent remaining for the other, and you don't really have to fill in the rest of those columns as long as we know that. So we know after 6 days, that's one half-life, that's 50% remains. 12 days, that's two half-lives, 50% of 50, or half of that remains, 25%. We know after 18 days, right, 6, 12, 18 days, we have 12.5% remaining. 24 days, another half-life. We have half of that, 6.25%. And then after 30 days, we have 3.125% of the iodine 131 remaining. So with only 3.125%, we know how to go through 1, 2, 3, 4, 5 decays. 5 decays times 6 days gets me my 30 years. This table lets you do that. Okay, so 30 days.